Okay, I hope that each day as you're doing these assignments, you're getting better at mixing together different types of our derivative rules. So in this assignment, you can see we're going to practice especially with exponents and logs. So our four rules that you've already seen are here at the top of the assignment. And now keep an eye out as we go through the problems that sometimes we'll need to add a chain rule. Chain rule does not apply in question 1, so we know that we have this multiplier of 2. Remember that just like our limit laws, we can move the constant coefficient out in front of the derivative, and then we could put that back in later. So we'll bring out a 2 and just do the derivative of x to the 7th, and that is a power rule when the base is the variable and the exponent is the constant. So you could right away, of course, write this as 14x to the 6th. G prime, again, we can keep the 2 out of the derivative, and then this is an exponential term because the exponent is the variable. So the derivative of a to the x is the rule we're using here. The derivative of 7 to the x is 7 to the x, natural log of 7. And then if there were a chain rule, then we would multiply by the chain rule. But when it's a single x, we can see that the derivative would just be a 1. So this term can stay the way it is. You could rewrite the order, but remember not to make this 14 to the x. That, of course, would change your results. And for h, the derivative of a logarithm in base 7 is 1 over x times the natural log of the base 7. In number 2, the derivative of e to the x, of course, is just e to the x. So some repetition here. The derivative of a to the x is, in this case, a is 2, so 2 to the x, ln of 2. And the derivative of the absolute value of x is, of course, just 1 over x. So nothing having to do with a chain rule yet in those problems. But here we have a chain rule. So the derivative of e to a glob is e to the glob times the chain rule on the glob. So the chain rule would be a 3. And of course, we would move that coefficient, I hope, out in front. And here we have a chain rule because we've got the natural log of a glob. The natural log, if it was just x, would be 1 over x. So the natural log of a glob is just 1 over that glob. Now we have to multiply by the chain rule on that glob. So that brings out a 3, and you will quickly, whoops, I'm doing the wrong function here. Let's just reverse instead of erasing here. I'm actually doing h prime first. And every time we do this derivative of a natural log with a chain rule, look for canceling. So you will quickly come up with some theories about what happens when you do the derivative of a natural log of a glob. Don't forget the chain rule here. All right, so now I have to go back to the one I missed here. The derivative of this exponential term. So think of this like a to the x. The derivative of a to the x is a to the x times the natural log of the base. But now we're not finished because our exponent is not just an x. It is a function of x. So it has its own derivative. So we have to do a chain rule. So again, if you rewrite this, make sure it's very clear. Do not change that to a 6 because the exponent only applies to the 2. All right, so just some repeated practice here in 4. Function f, the derivative of e to a glob is e to the glob, but notice what this glob is. This glob requires a chain rule. So now we've got to think what we're going to do for the derivative of the square root of 3x. And that, of course, requires a chain rule within it. So what is the derivative of 3x to the 1/2 power? So do you notice we're going to have to do 2 chain rules? So we're going to do the derivative of the square root first would be the power rule. we would bring down the 1/2 and reduce the exponent to negative 1/2. And then I didn't really allow any space here. We still have to do the derivative of the next inner glob. The derivative of 3x is 3. So we've got a little bit of work to do here with this function. And how do we want to rewrite this? That's really a matter of taste here. We could leave this e to the square root of 3x. Sorry, I really didn't leave you much room here. And we could handle this half, and this term with a negative we could put in the back in the denominator. So you could leave it with negative exponent, or you could rewrite it with a denominator. All right, g prime, also an interesting chain rule. So we have 2 to the x to the third. So you're going to have to find a little space here. So I think I will, as long as I can scroll over here. We have to do the derivative of 2 to the x to the third. So the derivative of a to the x first. So first we would do the same thing as a to a glob. So the derivative of that would be a to the glob times the natural log of the base, which is 2. I still haven't done any chain rules. This is just our rule of the derivative of a to the x is a to the x ln of a. So I haven't done any chain rule yet. So now I have to do the chain rule on that exponent, and that would be a 3x squared. And then we could rewrite this term. So if I transfer that over to our g prime of x. So the order of the terms there, really your choice. 2 raised to the x cubed times 3x squared. You could use parentheses here instead, and then a natural log of 2 perhaps. So your choice for the order. And now we have to do h prime, and the derivative of the natural log is 1 over x. So here the natural log of a glob would be 1 over the glob, and then times the derivative of the glob. So the absolute values are here to guarantee that we're only doing natural logs of non-negative terms. So 1 over x cubed, and then we've got to do a chain rule on that x cubed. So that would be a 3x squared. So again, remember a moment ago I said whenever you're doing the derivative of a natural log function with a chain rule, look for some canceling. So notice here an x squared will cancel with the x cubed, and what will be left will be a 3 over, oops, and I guess, did I do this? Yes. All right, I think we're okay there with a 3 over x. And now we're going back to get some review from our last unit of our derivative test so that we aren't allowed to forget. And I noticed a bit late here that I chose a graph where it might not be very clear what's happening. So we're going to agree that this minimum point happens at -3/4 and an inflection point here at -1/4. So just so we have some easy numbers to work with. And then there's another maximum point here at 0. There's of course another inflection point over here. We might as well call that 1. And another minimum point, let's call that 2. But I didn't really help you out with these, so we'll say -3/4 and -1/4 for the inflection point. You could have just estimated where you thought they were, if that should happen again. All right, so if this is the graph of f of x, we want to estimate the interval where f double prime would be greater than 0. F double prime of x greater than 0 is equivalent to saying f is concave up. So our inflection point will be important here. So from negative infinity to, I would say, it concave to the inflection point at -1/4, concave up, and then it's concave up again from 1 to however far we go here. So whether you do negative infinity here or -2 depending on how you're reading the graph, if you think that interval ends. Either way would be fine with me. And if this is the graph of f prime, now we've got to change our thinking. This is the graph of f prime. Where would f be concave down? So think again, if we want it to be concave down, we would want f double prime of x to be less than 0. That would happen when f prime of x is decreasing. So if this is our graph of f prime of x, we are looking for where is it decreasing. And that looks like the same answer that we just had from -1. Oops, sorry, not that far. From -2 to -1, it is decreasing. And then it is decreasing again from 0 to 2. I think that looks good. And if we are considering this to be the graph of f prime of x, and we're looking for where f would have inflection points. So inflection points of the original function, of course, is what we're looking for. So where does f have inflection points? That's where concavity changes. So concavity of f changes where f double prime changes signs. But that's not what we're given here. We're given f prime. So now let's think. What does f double prime do? F double prime comes from the slopes of this f prime graph. So this is where f prime changes from increasing to decreasing, or vice versa, or decreasing to increasing. In other words, in this case, where we have our local minimum and maximums. So this would happen at 3 different places. If this is our f prime, we've got a minimum point we agreed at -3/4. And maybe that was meant to be -1. I'm not sure how I was intended to read this graph. And at 0 and at 2 is where this graph appears to be changing from increasing to decreasing, or decreasing to increasing. So I think I want to go back and look at what I chose here in B. I'm not being consistent. If I decided that -3/4 was the local minimum of this graph, then I think here I contradicted myself, whether that was intended to be at -1 or at -3/4. But I think we want to be consistent throughout there. All right, sorry about that. All right, what do we have here? A little Austin Powers. And we'll move on. Sketch the graph of the cube root of x. Well, I made the graph paper wide enough here, since probably the numbers we think of as having the easy cube root would be 8, would have a cube root of 2, and -8 has a cube root of -2, and we would have 1, 1, and 0, 0. So if you wanted to be fairly accurate here, and we hope we know that this has a vertical tangent here. How do we know that? How we know that, of course, is when we do the power rule, 1/3 x to the -1/3. That has its variable in the denominator, so we can see that f prime at 0 is undefined because the variable's in the denominator. So in other words, that's what tells us that at 0 the tangent line is vertical. All right, so we want to sketch our graph of f prime on the same axis. We could do this visually, so we know there's no derivative at 0. So here the slopes of our red graph are very positive, and then they shrink down almost to 0 with this slow rising graph. So we want to have very large slopes, and then we want to get down to slopes that will get closer and closer to 0. So our derivative is something like that. On the other side, notice that our slopes are still positive on this side. So our slopes are very shallow here, close to 0, and then they rise up to become vertical over here. So again, you can think what happened. We started with an odd function. F is an odd function, and our f prime graph appears to be even. So we've seen that happen many times before. All right, let's get moving through some more derivatives. The derivative of a difference, we just do the difference of each term. So this would be cosine x minus the 8 comes out of the derivative, and the derivative of e to the x is still e to the x. No chain rule. Here we're doing the derivative of a linear term, that would be a 2, and the derivative of this a to the x term would be a to the x times the natural log of a. So no work involved there. In number 9, we have to be careful about the power rule for this term and the exponential rule for that term. So this 7 can come out of the derivative, and then we can do the power rule on the x to the 7th. When the base is the variable and the exponent is a constant, that's a power rule question. And this is an a to the x exponential term, so its derivative is a to the x times the natural log of the base. So quite a few 7s there. These two 7s we could multiply together. But that's the best we could do for 9. Several different terms here. The derivative of e to the x is still e to the x. The constant stays out in front. The next term is the 3 stays out in front, and then we do the power rule on x to the 4th. And our next term is an a to the x term, so just plenty of practice here so that this becomes second nature to you, and we don't spend a lot of time in the future determining which rule applies to which term. So in question 11, more of the same, derivative of e to the x, derivative of this is a constant. E is a constant, so the derivative of that term is a 0. And this term, the derivative of a natural log, is 1 over the glob. And this one has a chain rule on the glob. The derivative of 9.3x is 9.3. And notice what cancels there. So we end up with e to the x minus 1 over x. The derivative of this log in base 3, our rule is 1 over the glob times the natural log of the base. And then we can't think we're finished here because the 7x needs a chain rule. So that 7 will cancel with that 7. And then we're going to do, I'll switch colors here, then the derivative of the next term, the derivative of a constant, so that will be a 0, and then we have the derivative of e to the x is e to the x. So what did we end up with? 1 over x ln of 7 plus e to the x. And hopefully this isn't going too quickly. The derivative of an a to the x term is a to the x, natural log of the base. This term, think of it as a power rule. The cube root, think of it as a 1/3. So I'm going to do the power rule on the outside to the negative 2/3 when I subtract 1. And I'm not finished because there's a glob on the inside, so we've got to do a chain rule on that term. So we should do a little bit of rewriting there. This would be a 2/3 if you prefer, it's up to you how you decide to write this, cube root of, and then you could write this as 2x squared, or you could make it 4x squared. This next term has a monomial denominator. Remember that the easiest method is, if possible, let's just subtract exponents. Let's divide that x to the third into each term of the numerator. So subtract exponents. And then we just need to do the power rule on each term. 4x cubed minus 12x to the negative 3. There's no chain rule involved. These are just x's to the first power. And we're getting there, almost ready. On our first term, we don't need a chain rule. This is our a to the x rule. The derivative is 2 to the x, ln of 2. And then our derivative of another a to the x term. So it would be 3 to the glob, natural log of the base. But then we're not finished, because that exponent has its own derivative. So the chain rule on that term would be a 4. So how might we rewrite that? The only thing we could do here is to move the 4 in front. The natural log of 3 is also a constant, so you might move that out in front. So that might be the most common way you might see that one. And now we have to do a first and a second derivative, but not too much to do here. The derivative of e to the x, of course, is e to the x, and the derivative of negative x is negative 1. So our second derivative, the derivative of e to the x, will just continue to be e to the x, and the derivative of our negative 1 would, of course, be 0. And I think we're finished.